Assalamualaikum and hi everyone. We are from group 1 and we will be presenting about supercapacitor. Do you guys ever heard about supercapacitors? Supercapacitors are advanced energy storage devices that bridge the gap between conventional capacitors and batteries.
But before that, let's dig into the history of supercapacitor. For the 1915s and until 1960s, for the early concept, the first theoretical idea for supercapacitor were explored, focusing on their electrochemical properties. Next, move to the 1970s for the commercial development, that the modern supercapacitor was patented in 1971 by Standard Oil of Ohio. And then we move to the 1980s until 1990s, expanded application, which is supercapacitor found practically used in small electronic like VCRs and clocks, marking their growing importance in consumer electronics. And for the 2000s, in high power applications, that these devices began powering applications requiring bursts of energy such as the wind turbine and regenerating braking system. And the 2010s until present is modern evolutions that advance in energy density and hybrid design make supercapacitor critical in fields like transportation and renewable energy system. Now, I will explain about basic design of supercapacitors. As you can see the diagram below, it's referred to the number that typical parts in the supercapacitors. As a number 1 is a power sources that supply energy to charge the supercapacitors. Number 2, collector, that the conductive layer, typically metal, that transport electrons between the external circuit and the polarized electrodes. Number 3, polarized electrodes that provide a large surface area for charge storage. And number 4, double layer that represent the separations of positive and negative charge at the interface of the electrode and the electrolyte. And number 5, electrolyte that contain ions, which is both positive and negative, that enable the charge storage and transfer process. And then now lastly is a separator, number 6, to prevent physical contact between the two electrodes while allowing ion movement within the electrolyte.
Hello, for my part is type of supercapacitors. One of the supercapacitors are electrochemical double layer capacitors, which is EDLC type. The characteristic of EDLC are they have activated electrodes which are carbon. Then, they have extremely high capacitance due to large surface area of porous electrode. And lastly, they have non-Faraday, which means that there is no electron transfer. Next, why EDLC have double layer? It is because the electrode and hole are electrically attracted and creating an order state between the solid electrode and the electrolyte. And then why the electrodes are porous? It is because the effective surface area is very large, which enables the higher charge of the storage. The second one is pseudo-capacitor PC type. What is PC type? It is a type of supercapacitor that stores the electrical charge electrochemically through highly reversible redox reaction. It has higher energy density, but it has lower cycling life. The electrode material are typically made out of transition metals, conducting polymers, or compound with O or N functional groups. They also made out of metal sulfide, metal oxide, metal hydroxide, metal nitride, and conducting polymers. The example of metal oxide are ruthenium 4 oxide, nickel oxide, and manganese oxide. The conductive polymers, the example are polyaniline and polypyrrole. How pseudo-capacitor works? It works as a store of electrical energy by transferring the electron charge between electrode and electrolyte through redox reaction, and also they have electrosorption and intercalation process that called as pseudo-capacitance. The last one is hybrid capacitor. What is hybrid capacitor? It is another class of supercapacitors that combine EDLC type material, PC type, or battery type. Battery type is basically the one have a lithium ion or sodium ion. So they have 3 types of hybrid capacitor. The first one is hybrid capacitor with pseudo-capacitive and EDLC behavior. It combines the pseudo-capacitive material with ADLC behaviors. The second one is battery-type hybrid capacitor. One electrode exhibits as ADLC or pseudo-capacitive behavior, while the other type is battery-type electrode store that charge through the Faraday reaction. And the last one is asymmetric hybrid capacitor. It uses a pseudo-capacitive metal oxide cathode (MEO) and ADLC for the anode for the activated carbon.
Next, I am Danisha and I will explain about the charge storing mechanism. So the first one is electric double layer capacitor EDLC. This mechanism relies on the separation of charges at the electrode-electrolyte interface without chemical reactions. It is purely electrostatic in nature. So the process is, when a voltage is applied, ions in the electrolyte are attracted to the electrode surface, forming a double layer of charge. The first layer is composed of charges on the electrode, while the second layer consists of oppositely charged ions from the electrolyte. These layers are separated by a nanometer scale distance. So the key characteristic is the materials. High surface area materials such as activated carbon are commonly used. Energy storage. Energy is proportional to the electrode surface area and inversely proportional to the distance of charge separation. And the durability, EDLCs exhibit an extremely high cycle life due to the absence of chemical changes in the system, and this is according to the Conway 1999. Next, I will continue with the pseudo-capacitor. This mechanism involves fast, reversible Faraday redox reactions on the electrode surface. These reactions enable charge transfer between the electrode and the electrolyte. The process is, ions from the electrolyte interact chemically with the electrode surface via redox reactions, intercalation, or electrosorption. This chemical interaction allows pseudo-capacitance to exceed the energy density of EDLCs. The key characteristic is materials. Transition metal oxide, for example, ruthenium oxide, and conductive polymers, for example, polyaniline, are frequently used. Next, the energy density, higher than EDLC due to additional energy from the redox processes. And lastly, the applications, ideal for devices requiring higher energy storage capabilities compared to EDLCs, according to Simon and Gogotsi, 2008. The third one is hybrid mechanism. Hybrid supercapacitors combine EDLC and pseudocapacitor mechanisms to achieve improved energy and power density. For example, asymmetric supercapacitors. It combines an EDLC material, for example carbon, for one electrode with a pseudocapacitive material, for example transition metal oxides for the other. So the key characteristic is provide a balance between high energy density from pseudocapacitor and high power density from EDLC. And the hybrid designs are often based on advanced materials like graphene and carbon nanotubes, according to Miller and Simon 2008. So these two photos are the example of EDLC and pseudocapacitor.
For this part, I'm going to talk about the advantages and disadvantages of supercapacitors compared to batteries. So, supercapacitors have several advantages when compared to battery. Firstly, they offer faster charging, allowing them to be fully charged within seconds or minutes, compared to batteries which often take hours. Secondly, supercapacitors provide a higher power density, enabling rapid energy delivery and absorption, making them ideal for applications such as regenerative braking in vehicles. Additionally, they have a longer lifespan, lasting millions of charge and discharge cycles, unlike batteries which typically degrade after 500 to 1500 cycles. Supercapacitors also operate effectively across a wider temperature range, from -40 degrees Celsius to 65 degrees Celsius, unlike batteries which may struggle in extreme conditions. Furthermore, they are eco-friendly, containing fewer toxic materials, making them easier to recycle compared to traditional batteries. However, supercapacitors also have notable disadvantages. They have a lower energy density, typically storing much less energy than batteries, which limits their ability to power devices for extended periods. Another drawback is their higher self-discharge rate, as they lose stored energy quickly when not in use, unlike batteries that can retain a charge for weeks or months. Supercapacitors are also more expensive on a per watt hour basis due to advanced materials and manufacturing processes. Lastly, they have voltage limitation, with individual cells having low maximum voltage requiring additional circuitry to achieve higher voltages. In conclusion, while supercapacitors excel in fast charging, durability, and environmental benefits, there are lower energy density, high costs, and limitations in long-term energy storage restrict their use in certain applications compared to batteries.
Let's continue with the fascinating application of supercapacitors, the feature of fast and efficient energy storage. Supercapacitors are unique because they store energy electrostatically rather than chemically, enabling them to charge and discharge rapidly. This property makes them incredibly versatile across various industries. Firstly, in energy storage and backup, supercapacitors are used in uninterruptible power supplies and help stabilize power grids by providing quick bursts of energy. In electric vehicles, they enhance efficiency through regenerative braking system, capturing energy when vehicles slow down and delivering powerful boosts during acceleration. For consumer electronics, you'll find them in devices like smartphones and cameras, ensuring stable power delivery and extending battery life. In renewable energy system, they smooth out fluctuation from solar and wind power, storing excess energy for later use. Industries also rely on supercapacitors for pulse power application, like operating cranes or laser, where short, intense energy bursts are needed. In smaller technologies like wearables and IoT devices, supercapacitors power smartwatches and sensors using energy harvested from motion or light. Lastly, in aerospace and defense, supercapacitors are invaluable for satellites and military systems, offering quick energy delivery in critical situations. In summary, supercapacitors are paving the way for smarter energy solutions, offering fast charging, high power and reliable performance. As technology evolves, their role in modern application will only expand.
That's all from our group about supercapacitors. Thank you.